Welcome everyone. I'm Maciej Matyka, and I'm here today to present you the tutorial on GPU computing and implementation of some sort of simulations on fluids, but not only, also on diffusion and reaction problems using compute shaders. And this is because Robert has asked me to do that before the LBM in Kraków. Because he has seen this probably some years ago. I was working with this subject, and because of Robert asking for that, I came back into the subject, and I might say that today in 2022 is much more interesting than it was 5 years ago for me. And I will try to explain why and try to convince you that doing shaders is really very interesting from many perspectives. But that will not be completely tutorial in which I will write you a code or anything like that. I have prepared some two written tutorials so that you can read after this workshop, so you can relax. You don't have to understand everything. You can get it later reading by yourself. So where do we start? So because I was working some years ago with compute shaders, I found it very difficult to implement shaders from scratch, because the usual way is to do OpenGL, and OpenGL is the low-level library, which is there is a lot of problems with it, and I found it not very nice. I mean, I implemented shaders in OpenGL, but I didn't like it. I left the subject, and this is why I moved to some high-level library, and this is OpenFrameworks, and this is a library of my that I chose. So I will tell you a bit about GPU in general for those who didn't know a lot, about the shaders and the philosophy behind, and about the OpenFrameworks, the framework that I use, and then move into how to implement LBM. But this actually will not be that important after what Robert has done before. And then there will be some small surprise for Robert. Okay, so what is GPU? So for those of you who don't know, if we have a computer, the usual processor is CPU, is a central processor unit, which is doing all the work. But at some point, when computer graphics was evolving, people has found that on the computer graphics card, there is some processor that can do parallel instructions in parallel, so it can execute the same threads for many copies, and so this is vector processor. So GPU is something that probably every one of us has in his pocket, so in on his mobile phone or in the personal computer or in notebook. And this is, so you can see it, if I wanted to show you what GPU is, for people who don't know and didn't see, if this is your computer with CPU unit, so CPU can call some instructions that are placed on a GPU, which is on computer graphics card. So this is your graphics card, yeah? So sorry for my writing, but I'm not very used to this tablet. Okay, so GPU is outside of your normal operating system. And this is important for this talk, because the most problematic part in writing shaders is not writing shaders itself. It's about actually about copying data from CPU to GPU, calling the procedures and so on. So this is what GPU is, and this is how I see it. Now, why compute shaders? So if you write your code on CPU, you can of course parallelize it, but CPU can have some eight units, I mean 8 cores or something like this. So GPU can have thousands, so this is why GPU. We want to run fast simulations. And why compute shaders? So this is because of my interest in computer graphics also. Because if you want to run some real-time simulations, so simulations that the user can interact with, or you think of writing computer game with a simulation in the background, or you want to actually, I don't know, prototype some simulation, so see the result very fast and then later compute on some sort of serious machine, then Compute Shader is a very good choice. Of course, you can do the same in CUDA or in OpenCL, but you will find some problems with fast data transfer between computer graphics and the calculation procedures. With Compute Shaders, this is all solved. And the Compute Shader is a normal shader. It's like vertex or fragment shader in computer graphics, but it does not operate on textures directly. It can, or on fragments, or on vertex. It can operate on any data you want. And so now I will move into OpenFrameworks tutorial, and this is the part I will not cover very much in my talk here. I will try to convince you to read the article here, but first let me ask you for something. I have to open Firefox, which doesn't want to open now. I don't know why. Okay, I have a Firefox here. I will open the OpenFrameworks website so that you can do the same for yourself. You can download OpenFrameworks from here. It's free, open, and so on. Now, if I play the video here, it will show some OpenFrameworks possibilities. So this shows what the library can do. And my question is whether you can hear the music in the background. Okay, can you hear the music?
Yeah.
Yeah, okay. So I will just move very quickly through this OpenFrameworks demo reel. Okay. Okay, so this is multi-graphics and so on. I mean, video multimedia library, which is really very nice. And now if you go to the mathematica-medium.com website, you will find some two newest articles. And the first one is GPU Computer Shader in OpenFrameworks tutorial, part 1 on Grace Code Reaction Diffusion. And this is what I want to start with. So if you download your OpenFrameworks library, you compile some examples here, you will find out it's very simple. Now I will show you in some not very detailed manner how to implement and how the shaders actually work. So now let's go quickly through this, and then later you can read more in the background. So my view on CPU and GPU is as you have seen before, but an additional thing is the connection to the screen, to TV. So graphics card is directly putting the pixels on a TV through your HDMI cable, and it does not go through CPU anymore. So if you compute on computer graphics card, you can directly push your pixels into the screen, and this is the key point. Because then if you compute on a GPU card, you don't have to get back the pixels into CPU. Now the OpenFrameworks, now I will open it larger. Now OpenFrameworks code is very simple. It's object-oriented code. So you have your main class, which is in the very basic startup project is just 3 functions. So you have 3 methods: setup, update, and draw, which is obvious. Setup is for setup, draw is for drawing, and update will be for calculating anything here. So we will execute our shaders from update. Now we have this is the first file. So this is ofapp.h. So this is the header file. The second file is OpenFrameworks app.c++, and this is just now an empty file with the setup, update, and draw functions. Now I start, of course, to start the whole thing, I also need the third file, and I will not come back to this file because it's very simple. It's just main CPP, which is opening a window of some size and running this application of OpenFrameworks. So now you can see how simple the structure of the code in this library is, and this is main point. Now we continue with what do we want to write. So I want to write the Grace Code diffusion reaction system. This is very simple. I will open Carl Sims' website, which I really like. So Carl Sims is an artist who is working with such stuff for the computer multimedia and vision. And there are those two equations which we have to solve, and we will solve them in. So this is finite difference for some diffusion reaction system, and we will just directly calculate them on a grid. And we will not do anything more than those two lines of code with some calculating of the Laplacians of field A and B. So we have four fields, A prime, B prime, A and B. Why primes? Because we do some ping pong here, so we will calculate A prime and B prime from the field A and B, and so on. So we will swap. And this is why it's interesting for Lattice Boltzmann people, because we do the same with Lattice Boltzmann usually when we want to do GPU. I mean, in the simple case, we use ping pong. But here we will do reaction diffusion. So now, just to start with the shader story. So we will use those two equations, where Laplacian A and B will be calculated later. So I will skip the physics part here, and let's come back to the shader. So now I continue by putting the same, putting new code into the shader. So you will have the everything clear and nothing will be skipped. So I will just increase and increase the size. So this way, this article comes very large. And now, so we start with the definition of the system size. So we have width and height of the of our window 1280 by 720, and I will use the same for the GPU LBM grid. So I will have the pixel to grid 1-to-1, just to not. But the scaling is very simple. Later you can scale anyway to larger size. So now we put some buffers. So buffers are objects that will be put on a GPU. So you start with, so we have those four buffers, A1, B1, A2, and B2. And first, I also allocate the same buffers on CPU just for the initialization. Later, I can even skip this if I don't want. But I use it for initialization. So let's move on. And now in the OFAPP C++, in our class of OpenFrameworks, we initialize our fields. So I will initialize with some random numbers. It's very simple. A1 will be 1, A2 will be 1, B1 will be 1 with some spots which are 0, and B2 are 0. So let's not go into physical details of what those fields mean. If you do this random, then you will get very nice pictures. So now let's allocate buffers on GPU side, and to do that we use the allocate method of the shader storage buffer object. So if A1 is a buffer object that we have created in our class before, then we can use allocate function just to allocate a proper array on a GPU side. Now, if we call this on a GPU, the memory is allocated. And we also use our CPU array just to initialize. So as you see, I could skip it, but even use it. So Robert will not like it. He likes to optimize things, as I have seen in his talk before. But so I don't care, because I have a lot of memory on CPU now, and I don't want to spend my time on optimizing here. Now, we need to tell the shaders which buffers the shader has to use. And for that, we use the binding procedure. And the binding can be understood as connecting wires. So you can understand that on the left-hand side on this picture, you have A1, A2, B1, and B2 arrays. On the right-hand side, you have 0, 1, 2, and 3 spots. So Polish scientists will understand spots as spots for publications, as our minister is expecting to fill. But here we are not filling spots for papers. We are filling spots with proper buffers. So we are connecting a buffer into a spot. This way, each shader on our graphics card will know which spot brings him to which buffer. So binding is very simple. We just bind our buffer into the specific number. So for instance, A1 here will be buffer 0. I mean, the buffer A1 will be in a spot 0. Buffer A2 will be 1, and so on. Okay, you need to understand this to understand later how to do ping pong. So this is why I introduced this. Now we want to see the things, so we will use a texture. The texture is simple. We create OF texture of the name textura. Now, so textura in Polish means texture. So now we have this object created in our header, and now we allocate and bind the texture. So the text to allocate the texture, we just use the function allocate, and to bind, we bind as an image into the number 4. Now you can see before we have bindings for 0, 1, 2, 3, and now the 4th will be our texture. And you can use more. So you can have as many bindings as your card can allow. And now to draw the texture, you use textura.draw. So people who worked with OpenGL before can see how much of the headache I don't have to put into the code if I use OpenFrameworks, because a lot of work is done in the background. So now the textura draw, just draw the texture. Now we will have the culmination point, so we will implement the shader. Now to implement the shader, we need to first have it in our class. So we do OpenFrameworks shader. Now in the C++ code, we need to set up shader from file. So we load the shader from a file, because this is how it is organized in OpenGL and other frameworks. So we have to load a shader code into GPU and compile there. So GPU will do the job on the GPU side. So we need to load the this shader and link it. So the link is doing all the job. If any like an error is in the shader, then it will be given by this link program method. Now we move on. As you see, nothing more. We already set up a shader with 3 lines of code. This is amazing. If you do it in OpenGL, you have to spend a lot of more. Now, to do ping pong, now you have the picture. To do ping pong from A1 to A2 and from B1 to B2 and so on, we need to swap buffers, and we will do this by reconnecting wires. So we don't copy buffers, we will not swap, we will not run 2 codes for this. We will have one shader, but shader will not operate on buffers, it will operate on numbers that these buffers were connected to. So now to do that, we just do, this ping pong is here. So we are introducing the C, which is a number 0 or 1. So we swap 0, 1 by each from doing each execution, and then we bind A1, A2, B1, and B2. So from these little expressions, you can understand that A1 is 0 or 1, then A2 is 0 or 1, then a B1 is 2 or 3, and so on. Now these are bindings for computer shaders. Now for the shader itself is run by calling dispatch compute function, and now this function we start with shader begin, then shader dispatch compute, and shader end, and then this dispatch compute means execute. Yeah. I don't know why it is called dispatch compute, but anyway. So then we have these 3 parameters, and these are the sizes of our blocks. So for those who don't know the GPU computing, so this is running anything on GPU is organized in such a way that we are grouping our threads together. So we have the instances of our compute shader that run in parallel. So basically by changing this, you can basically increase or decrease the speed of execution, depend on your graphics card, and this is how it looks. If our system size is width over height, then we subdivide each of our system into like W by 20 and H by 20 size. So this times this is the working group size that will be run in parallel on your graphics card. Of course, you want to have it the largest possible, but this depends on your graphics card and the possibilities of your hardware. Now we move on into compute shader. So last but not least, compute shader, how to implement it. So we will use GLSL language. So this is language is normal language for like OpenGL and not only shaders. So the version of OpenGL, the minimum version is 4.4 that you have to have in your system. And the compute shader is actually very simple. It's very similar to C code. So you have a void main and so on. So now we start with empty shader. We put our bindings. So that means that the shader will receive bindings of this for these numbers and will put these names. So this name has nothing to do with the names on CPU side. This A1 name is here internal for CPU, for GPU. Anyway, so but the shader knows that for 0 he will have A1, for 1 he will have A2, and so on. Now we also have our texture. This is image 2D. We'll only write to this image, and also we have this layout for local size X, local size Y, and so on. And this is the number of working groups. So the 20 means that we'll have 20 working groups of some size that dispatch compute has sent to GPU. Okay. Now we will use some helpful function. This is periodic. I also didn't really optimize it. This is just for because we will search for neighbors, and in the neighbors on the right hand side, like outside of our domain, then we'll plus an X, and if it will be from the left hand side, we'll minus an X. That's all. That's just for people who didn't work with GLSL to show how to implement functions in it. It's simple. Now we have the color function. This is helpful function for coloring stuff to make it more beautiful in a sense. So instead of doing some shading from 0 to 1, I will code the color. So for people who don't know this technique, it's very simple. We use some cosine and sine functions, and just by using this parameters, we will get in return 4-dimensional vector of a nice color. This technique is from Inigo Quile's website. This is a Demoscene guy who is doing the very nice stuff and also showing, for instance, how to do nice palettes. So from 0, 1, you can do palette like this. So if you don't know it, you can use it in your codes. It's the knowledge is here, and just go to this website of Inigo, and you will find out very nice stuff here. And these palettes are very useful. So I also use them to make it nice. Now, so I use this color function. Now let's go into simulation. So the simulation is actually very simple. We start with taking the I and J, so the position in our grid. And to get position, we get the standard variable global invocation ID. And we take X and Y. So I just use some hard-coded constants. I calculate one-dimensional mapping of this I and J and do the simulation. So I have some parameters, just very simple. So these parameters are taken from somewhere. And then I recalculate indices for all the neighbors. So I take the neighbor on the right, left, up, and below, and I use periodic function I just introduced. And now if I do this, I can calculate Laplacian. So I calculate Laplacian for A and for B. As you see, this is normal C code. There is nothing about shaders and GPU. It's very similar to what we do with CUDA, of course, but anyway, this happens in a shader. Now the grayscale model is here, so we use just those two equations that I shown at the beginning, and the visualization is here, which is just that simple. We take A2 and B1, just recalculate some float point number. I hard-coded this 1.51 and 1.062 to make it visible, and then I take color. And image store is a standard function in compute shader, just store a number in texture. The final code is just this. I will not go through this because we already done it, and this is the result. So if you now look on the screen, this is the video of captured from the real-time simulation, and now I will go into real-time stuff just to show you this how it works in real time. So we take this grayscode, just make it. So this is how OpenFrameworks works. So I do make and make run release. Now if I, okay, so now we have it run on my GPU here at my computer. And if we wait long enough, then we will get very nice results. But I will not do that. I will move on and just show you how this can be used and how can be transformed. So if we have shaders, then there is no problem with doing fancy stuff with coloring and image processing. So for instance, we can do simple bump mapping, and I want to show it to you because it just looks completely different if you put some light into the result like this. So if you have two-dimensional scalar field and you put some light on, then it looks three-dimensional, which is maybe very nice to see some details in a simulation, but also for some people just nice to watch. So this is again this grayscode I showed you before. So if you go into this tutorial, you will definitely understand how to do stuff like this. Now, if we want to do Lattice Boltzmann, then there is, of course, the story is very similar. So you have to go through this procedure of binding stuff and so on, and copying buffers into GPU. And this you can do by yourself, but I recommend you to see my second tutorial. So you can find it here by clicking on part 2. But before we go into part 2, I go into the OpenFrameworks LBM just to show you this, how it looks like in real time. Okay. So this is Lattice Boltzmann, the same that Robert was showing just a second before, implemented with the driven cavity, and actually it's the same model. It's BGK in 2 dimensions. I have a shaders, so this is why Robert was interested, probably also, because on my website you can find shaders with cascaded Lattice Boltzmann version, also with some Smagorinsky turbulence model, and then all this stuff is happening much faster. But anyway, so because this is just coding into the standard Lattice Boltzmann. But anyway, so now this runs real time. I will not move with mouse or anything. There is no interaction, but just quickly go through this tutorial for fluids. And now this is a work for you to understand, but the motivation is that this tutorial is written such that you can have the 3-dimensional flow. So I go through the same procedure. So I show you the initial OpenFrameworks code, and then step by step, by initialization, all the buffers, you can go through and just implement your own Lattice Boltzmann in 3D. So I hope this is encouraging for everyone just to put the hands on. And if not, then I will show you the results. So this is the complete code. It is with the description. So I cannot do it now because I have 2 minutes, and that's besides, this is pointless. To understand shaders, you already know from grayscode. To understand Lattice Boltzmann, we have all the other nice talks and the introduction by Robert. Now I go to this 3D Lattice Boltzmann just to show what to expect. So now if we go to compute shader, and this is 3D, so this is 8. Okay, and make, just to make sure I have everything. Okay, run release. So this is now happening in real time here on my computer, and this is 3-dimensional Lattice Boltzmann. So it was a headache to actually find out nice properties of this visualization, just to see 3-dimensional effect, because these are all particles and they blend, and they have to, okay, I put more, and they have to, okay, blend. Okay, so now you can see this 3-dimensional effect. We can move in and just see from the inside. It's very nice that it happens in real time. So I basically can think of some applications where people want to see rapid result of the simulation. Okay, so now I will move on into the last part, and this is, okay, so that was Lattice Boltzmann fluid, and now the surprise. So now the surprise will be about something I wanted to prepare for the end, and I failed. So I wanted to do 3-dimensional multiphase flow, And this is because I did two-dimensional multiphase, but I will not show. You can see on my YouTube channel some results. But I wanted to do three-dimensional, and three-dimensional Lattice Boltzmann. Okay, it works. The multiphase also works. What I felt is the speed. So the why, and not because of the Lattice Boltzmann and of multiphase, but because of visualization. So the problem is that with multiphase, what you get from the result of your solver is three-dimensional volume object of density. And to visualize it, you have to do either some fancy, or not very fancy, but not that easy to implement Merging cubes algorithm or any other surface extraction algorithm. And but I found it more interesting in the context of shaders to do ray merging and some sort of ray casting of the volume. And actually I did it and it works, but I had to really so I wouldn't say this is the state-of-the-art solution. And what you see is a lot of mistakes and a lot of prototyping and not very much physically accurate lighting and so on. But I did it. And I found it not very nice. I mean, it doesn't look that nice I was expecting. And I found it very, okay, how to say, very 8-bit, okay? So I thought that maybe not, I will not show it as a scientific result or a result for, to encourage you that this is scientifically nice and so on and accurate. I will show it in other perspective. So this is for Robert, and every one of you will be, and this is for run release. So this is multiphase 3D Lattice Boltzmann with on compute shaders. So let's have a look. Okay, and as you can see, what I'm also suffering of is the disappearance of droplets in single fluid multiphase Lattice Boltzmann, which I have to solve. So thank you very much, and that's it.